In this video, we're going to be talking about a different way we can use the Pythagorean Theorem. So real quick, just looking at our Pythagorean Theorem, if we square the two legs of a triangle and add it together, and compare that to the hypotenuse squared, in the Pythagorean Theorem, in a right triangle, those two values are equal. So when we square the two legs and add them together, in a right triangle it's equal to whatever the hypotenuse is squared. But if we tweak this, if we just change this formula slightly, if we actually take away the equal sign and put in a different sign, an inequality sign specifically, we're going to be able to figure out if it's a different type of triangle. So the Pythagorean Theorem with an equal sign only works for right triangles, and the new stuff is this. If we do the same thing to the legs, if we square their values and add it together and compare that to the hypotenuse squared, if the hypotenuse squared is less than the legs squared and added together, that means that the hypotenuse is smaller, right? We get a small triangle, an acute triangle. So just by making that slight change there, we're now talking about a different type of triangle. So real quick, we'll draw a picture and try and emphasize that point. So right here I have an acute angle, an angle less than 90 degrees. The side opposite from that angle is affected by this opening. The bigger the angle here, the longer this side opposite from it. The smaller this angle, the shorter this side opposite. So if I have a small angle, then I have a small side. And if that side is supposed to be the biggest side on our triangle, then I have a small triangle. I have an acute triangle. And by comparison, if we do the exact same thing, if we square each of the smaller legs there and add it together, and if we square the hypotenuse and that hypotenuse squared is bigger or greater than the legs squared and added together, then we have a big triangle. We have an obtuse triangle. So that would look like this. If I had drew myself an obtuse angle here, well, now I have a much longer side across from that angle. And if I'm talking about C, that means I'm talking about the longest side in a triangle. And if the longest side is much larger than the other two sides, even if they're squared and added together, then I have an obtuse triangle. And that's created by that obtuse angle. Alright, so let's do some examples here. Again, you need to remember that C is always the largest value. In a right triangle, it's always the hypotenuse. But if we have an acute or an obtuse triangle, it's always going to be our largest side. It's always going to be C. So looking at these three values, think to yourself, which one of those is C? Hopefully you came up with 8, because that's the largest value. So that must be the longest side. It must be C. So I'm going to say A squared is 6 squared. I'm going to say B squared is 7 squared. And I'm going to say C squared is 8 squared. So when I simplify, I'm going to think about how this expression here, these two values, compare with this value. And that comparison, I want to leave blank. It could be equal, it could be greater, or it could be less than. I don't want to say exactly until I'm all the way at the end, and that will be our last step. So 6 squared is 36, 7 squared is 49, so if I add that together I get 85. And then 8 squared is 64, so how does 85 compare to 64? Well, 85 is much bigger. So that means that our hypotenuse squared is less than So if the largest side, c squared, is still less than everything else, that's a small triangle, that's an acute triangle. I would suggest focusing on this value. Look at the inequality, which side of your inequality is pointed eventually at that value. And if the tiny side is pointed at that value, it's acute. If the big side is pointed at your c value, it's obtuse. So it's a lot easier if you're always looking at your c value, because the tiny side would correspond with a tiny triangle, an acute triangle, and the big side would correspond with a big triangle and an obtuse triangle. Alright, let's get rid of some of this stuff that's in my way here. One last thing that you always want to keep in mind when talking about types of triangles and figuring out what their values are is to always think, is it a triangle to begin with? So remember back when we were talking about how do we check to see if three values create a triangle? We always add up the two smallest values, so I'd say 6 plus 7. We're not going to square them when doing this check, so there's a difference there. If I say 6 plus 7, that has to be greater than that third side, 8. Well, in this case it is, so we do have a triangle, and then we do our test, which is an acute triangle. So always check to make sure you're dealing with something that is a triangle to begin with before you look at what type it is. All right. So let's do that on the next example here. So I take the two smallest values, add them together, and ask yourself, is that greater than 11? It has to be greater than. It can't be equal or less than. 7 plus 8 is 15, and 15 is indeed 11, so we know it's a triangle. Now we can see what type of triangle it is. So we'll always do that check first. So now we do our Pythagorean theorem. We square our values. Don't square them if you're checking to see if it's a triangle to begin with. Only square them when you know it's a triangle and you're looking at what type. So how does 7 squared plus 8 squared compare to 11 squared? 7 squared is 49. 8 squared is 64. If we add that together, we get 113. How does that compare with 11 squared, which is 121? Well, the hypotenuse squared is bigger, so we must be dealing with a big triangle. That would be an obtuse triangle. Alright, again, let's get this out of our way and deal with the next example. Now, sometimes they're going to try and trick you and give you some weird values with radicals. Try and remember that this is a decimal value. And sometimes it's not going to be incredibly obvious what c is. It's not obvious what the largest value here is. Obviously 3 is bigger than 1, but is 3 bigger than the square root of 10? Some of you might already know the answer to that question, but if you don't know, you gotta check, because you need to know what c is. You need to know what the biggest value is. So if you type into your calculator the square root of 10 and you get that decimal value, you get approximately 3.16. So now you can compare all your values. They're all in the same form here. So 3.16 is just slightly bigger than 3. So we know that the square root of 10 is going to be our c in our equation here. So again, check to make sure, is 1 plus 3 greater than 3.16? Yes. So we are dealing with a triangle. Now we need to see what type of triangle it is. So we're going to do 1 squared plus 3 squared, and how does that compare with the square root of 10 squared? Hopefully you remember by now that squaring a square root undoes itself. So all of that goes away and we're left with the number underneath. So we're just left with 10 after we square that. 1 squared is 1, 3 squared is 9, and 1 plus 9 is 10. So how does 10 compare to 10? Well, they're equal, they're the same value. So what type of triangle is that where they're equal? And we know that's a right triangle. So that's basically the lesson. Again, check to make sure it's a triangle first. Add your two smaller values and make sure it's bigger than that third value. If that's true, then do your Pythagorean Theorem inequalities and figure out what type of triangle. Is it acute, obtuse, or right? Aside from that, I'm going to show you a quick trick here. There are special right triangles that have values that are always the same. So if I have a right triangle, has a right angle, and the two legs have a value of 3 and 4, and it doesn't matter which one's which, as long as the legs are 3 and 4, we automatically know the hypotenuse is going to be 5. And if you don't believe me, substitute 5 for x and solve for this hypotenuse using your Pythagorean theorem. You're going to get 5 when you solve for it. And that's always going to be true. This is a special right triangle, and this ratio, 3 to 4 to 5, is always going to hold true. If you are solving for a leg, let's say this leg was unknown over here, but you knew that the hypotenuse was 5 and the bottom leg was 4, hopefully you would recognize that that has to be 3. That's that special ratio there. Or likewise, if you knew the leg was 3, but you didn't know the other leg, but you knew the hypotenuse was 5, hopefully you would recognize your special pattern and say, well, that's a 3, 4, 5, and I'm missing my 4. Or lastly, if you knew the bottom was 4 and the other leg on the left here was 3, but you were missing your hypotenuse value, hopefully you would recognize that your two legs are 3 and 4, and you could just jump to the conclusion that your hypotenuse length is 5 automatically. And in addition to that, you can have any ratio that's similar. Remember that similar ratios always reduce to the same value. So if I double each of my values here, if I have a triangle that's a 6, 8, 10 triangle, which would look something like this, the two leg values would be 6 and 8, and our hypotenuse would automatically be 10. Because that's in the same ratio as a 3, 4, 5. If I reduce each of these, if I divide each of these numbers by 2, I get back to my 3, 4, 5. So any similar ratio, you could double these values, triple them, square them, do all kinds of stuff to them. As long as they hold the same ratio, 3, 4, 5, it's always going to hold true that they're special values, and you can always fill in the blank if you recognize it. But if you don't recognize it, you can still use your Pythagorean theorem to solve for that missing value. But then hopefully by the end of your Pythagorean theorem you realize, oops, I forgot. It was a special right triangle. Likewise, you can have a ratio that's a 5, 12, 13. So it's only these two so far. And that's saying that the leg values are 5 and 12, and that the hypotenuse is going to be that larger value, the 13. And again, if you double each of these values, if I have a 10, 24, think about what that hypotenuse would have to be if I was doubling everything. It would have to be 26. So you see a triangle that looks like this, with the ratio 10, 24, 26. Hopefully you don't have to do any math to fill in one of these values if you just recognize that special right triangle ratio or that special pattern there. So, yeah, that's more on the Pythagorean theorem. We'll be getting into more special right triangles in the next video.